part of Einstein's special theory of relativity. It was a truly revolutionary discovery which illuminated our understanding of the universe. But, as groundbreaking as it was, it doesn't necessarily have to be complex or difficult to understand. In fact, I bet we could devise the key concepts ourselves. Einstein's special theory of relativity was composed of two postulates, or constituents. The first one, named the principle of relativity, simply stated that the laws of physics are the same in all inertial frames of reference. An inertial reference frame is an observation point in which scientists can understand physical phenomena and formulate laws. An inertial reference frame, simply put, is just what a person considers to be at rest. And mind you, I say considers because you can also consider it to be in motion relative to something else in the universe. Sounds like we're developing a theory of relativity. So Einstein said that the laws of physics work identically in any inertial reference frame, meaning one that's moving at a constant velocity, one that isn't accelerating, one that isn't speeding up or slowing down. Now, well, that's not too hard to prove. Just grab a chair, sit back, and watch how the laws of physics unfold. Nothing's happening. Now let's conduct the same experiment in a car. The speed of the car at this moment is constant, but what would happen if the driver decides to change the speed of the car substantially? In an instant, the laws of physics seem to act slightly differently. But if the car travels at the same speed, at a constant velocity, the same thing happens as when I was just sitting on the earth. Nothing. In both the reference frame of the car and the earth, I don't move. Although the car and the earth were moving at different speeds, but as much as I could see, the laws of physics were no different. So we can also say that the same would have happened in any inertial reference frame, and our logic wouldn't be any less reasonable. And that is the first postulate of Einstein's special theory of relativity. Einstein's second postulate stated that the speed of light has the same value c in all inertial frames of reference, and is independent of the relative motion of the source and the observer. Now, this may seem very straightforward to understand, but back in the 18th century, people had just realized that light had properties of a wave, and the other kind of wave they were familiar with was sound. Therefore, people concluded that light must also need a medium to travel through, and they called this hypothetical medium the ether. Now, how do you prove the existence of an ether? Well, Michelson and Morley, in the summer of 1887, had conducted an experiment using a device labeled an interferometer. So we don't know our orientation relative to the ether. We don't have an absolute frame of reference. We can't say that the ether either starts from here and ends there, but we know that we're constantly changing our direction. If there is a luminiferous ether, we must be moving relative to it. We should be able to detect a type of ether wind. If there was such a thing as an ether, then the Earth would pass through its orbit around the Sun. On Earth, it would seem as if the ether was moving. An interferometer, as shown here, measures the variance in the speed of light that would occur if there were such a thing as an ether. Light would split along two perpendicular arms, be reflected back to the center, and cause to converge in an eyepiece. But the way they noticed the difference in the speed of light was the shifting of the interference pattern between the photons. If light traveled at different speeds down each arm, it would reach the eyepiece at different times. If the ether wind was traveling in this direction, light would travel faster when it's facing the same direction as the ether wind, as compared to when it's facing perpendicular to the direction. However, when this experiment was actually done, there was no change in the interference pattern, telling us that nothing was causing light to move slower, which proved that light did not need a medium to travel. In any given reference frame, the speed of light would not decrease because the medium was traveling against it. The light was able to travel in empty space without a medium in motion. Light did not need a medium to travel through, which told us the speed of light is constant, meaning it does not change. There you have it, one of Einstein's greatest achievements, and we were able to explain it in a matter of minutes. Makes it seem kind of simple, doesn't it? The brilliance of this discovery lies from the phenomena resulting from the two postulates. Suppose you have a light clock which has two mirrors, both facing the opposite direction, and a light beam bouncing between them. The distance between these two mirrors can be denoted as d, and the time for light to cover that distance, t. For simplicity's sake, let's say t is equal to 1 second. When this light clock is with you, The light beam bounces between the two mirrors, covering the distance d in 1 second, giving us the speed of light, s, and we know that speed is equal to distance over time. Consider your friend also possesses the same light clock with him, yet he's traveling in a spaceship along with the clock. When your friend travels at a certain speed, the clock travels along with him with the same speed as the spaceship. While your friend is traveling in the spaceship, the light beam and the clock has to travel an extra distance in the same 1 second. That extra distance can be denoted as d, so we can represent the speed of light here as s equals to d over 1 second, in which capital S is greater than smaller s. But that can't be, because we know that from Michelson and Morley's experiment that the speed of light is constant. Looking back at our context, small s and capital S are equal to c. In order for the speed of light for both you and your friend to remain constant, something must give, and that something is time. Einstein's theory of special relativity states that time slows down as you approach the speed of light. The faster your friend travels, the slower time passes for him. Since the speed of light is constant but has to travel a larger distance, it will have to accomplish it in a much longer time. Theory of relativity broke the conventional understanding of time as a constant entity and proved that time, in reality, is different for different observers. Now, it's only natural to conclude such when you combine the speed equation and the fact that the speed of light is constant. Fortunately, it isn't easy to conclude from our day-to-day life on Earth, but if humans are able to travel near the speed of light in the future, it'll be thanks to Einstein's tremendous understanding of the universe that we'll know exactly what to expect.